Hi, this is Mike Casey, Director of Education with Home Inspection University. And today we're at a house, about 10-15-year-old home in the Midwest, and we're going to be inspecting the electric panels starting at the service. Now this one, we've got an underground service, comes up through a service lateral right here. This is a plastic conduit that feeds this, what's called a meter base. We've got a large enclosure here, and I'm seeing that we have two plastic conduits that exit this meter enclosure. So this is telling me that we most likely have a parallel wired service, which means that we're going to have most likely two panels in the basement that are service panels that are wired in what's called parallel off of this meter. So inside this enclosure, we're going to have lugs going this way, and then when these service conductors come in, we've got separate connections for both service entrance cables. And you can see here we have these big LB boxes that enter this meter hub. And this is the service lateral that goes underground out to the transformer that's in the street. So you can tell the difference. It's such a large one. When you have a big enclosure like this, that almost always means that you're going to have service entrance conductors in parallel going to two panel boards that are in the basement or in a garage or wherever they might be. Now this one, we've got some other components outside as well. And we can see this looks to be an added sub panel that we're going to open up in just a minute. And then this is telephone, cable TV, and so on, low voltage components that are connected here as well. So pretty typical for this location. And I'm seeing here, this looks to be our grounding electrode conductor. This is going to go to a piece of metal that's driven into the dirt, typically a rod. And you'll notice that the telephone and cable TV and so on will bond to this as well. That would be typical. You want everything to be all bonded together so it has equal potential to ground. So this is the right way to do it. On more modern panels, you're typically going to have a central point ground that's installed on the outside of this enclosure or the service equipment for everybody to connect to. So cable, phone, and so on, satellite, they all connect together at the same place. This is a close-up of the meter on this big, large meter hub and enclosure we were talking about. And one of the things I like to look at, although it's not required by the standards of practice for a home inspector, is I like to look at the rating for the meter, just so I know, all the different aspects of the service when I'm determining the capacity. Now this meter here, you can see it has the number 200 CL. That tells me that this meter is rated at a maximum of 200 amps. There's also a meter made that's called a 320 CL that I would typically see on, say, a 400 amp service. The other rating on this is the 240 volt. That's a standard in America voltage rating. All services are going to be 240 volts, and we maintain the 120 volt circuit by connecting a neutral to it. So pretty typical meter. Again, we're looking at 200 amp rating on that meter. So I know just by looking at this that the maximum capacity of any service in this building is going to be 200 amps because it's limited by the meter. We're going to inspect this, what looks to be an added sub panel on the outside of this house. We can see we just looked at before the service equipment, and this is a small sub panel. And we can see that it's an outdoor rated type of a box. And one thing you can see here is on the back where I'm sticking my fingers, there should be about a 1/4 inch space between the enclosure and the wall surface that allows the water to drain through. And a good tip-off that we're looking at an outdoor enclosure will be this awning-style cover that opens this way. That's to protect the interior components from moisture. And we're just going to pull off this dead front. I like to slap it with the back of my hand first and make sure that it's not energized. There's no unusual sounds coming from the panel. So we're going to pull this off, pull out the screw, and have a look inside. You want to just pull it off slowly. Try not to trip any breakers. This one we've only got one. Now this panel, we can see that we have our sub panel feeder penetrates the enclosure in the back of the box here. And the cable that's coming in, I can see that we don't have a cable connector or a stress clamp, some people call it. So that's a reportable item there. There should be a stress clamp around that cable connection or penetration to the box. And I can see that we have our two hots we have a neutral right here, and we also have an equipment grounding conductor that's over here. Now there's a 50 amp breaker in here, a 240 volt breaker. You can see it has the circuit tie for both the legs of the breaker. This happens to feed a hot tub that's out in the back of this house. And what we're seeing here is the two hot feeds. We also have a neutral, and that tells me that there's probably a 120 volt component in that hot tub. Most likely a light, or could be the pump, could be some other components. Now the branch circuit that goes out to feed that goes into a liquid tight conduit. That would be typical for outside. And I see we have two hots again, the red and the black, a neutral, and the neutral is separated here from the equipment ground. And the equipment grounding conductor, what they did here was just connect it to the equipment ground in the cable that's feeding the sub panel. Technically this is incorrect. What we should have here is a bonded terminal bar that connects to the enclosure, because we have to protect this metal box as well. This is protecting only the circuit that goes out to the hot tub. We have right now no protection for this enclosure should it become energized. So we should have a bonded terminal bar, which is basically just a bar with some slots in it and screws to hold them in place, that connects to this enclosure itself. And both of these wires should connect to that bonded terminal bar, so we're also protecting this enclosure. And another tip off when you're looking inside, that you're looking at an outdoor type of a box, will be you'll see that the back, where the mounting screws go, have built-in standoffs to help create that 1/4 inch gap between the can here itself and the exterior surface of the building. That's to keep any water from sitting behind the panel and causing deterioration to the enclosure. So right here we're missing that stress clamp, and here we should have a bonded terminal bar similar to this one for the neutral, but it should connect direct to the box and be separate from this neutral, because we always want to keep the neutral current separate from the equipment ground and any equipment that's downstream from the main service panel. So I think we're done with this one. We'll go ahead and put the cover back on. You always want to be careful putting the cover on. Try not to let it hit any of the breakers, because when they turn off, sometimes they don't turn back on again. And this circuit here, it should be labeled. There should be something, a little sticker on here that tells us what this breaker is for. Simply just writing hot tub would be fine, but all circuits are required to be labeled. And I think we're done here, and we can go ahead on inside. I'll see you in there. Hi, this is Mike Casey with Home Inspection University again. We were just outside looking at the service lateral entrance to this house. We inspected the meter base and also a sub panel outside, and now we're down in the basement of this home and we're going to inspect the service panels. And this home happens to have two of them. And you can see here are the service panels. Now the first thing that I want to look at is to make sure that we have enough clearance, what's called working clearance, around these panels, which tells me that we can safely inspect them. We don't want to have stuff in the way. We don't want to have to lean over things to inspect them. So generally what the requirements are is 30 inches wide of clearance, and the panels don't have to be in the center of that, but 30 inches wide, which is basically the width of a human, so we can get in and not be touching anything, and then about 36 inches deep, which is pretty much an arm's length to touch the panel, so that we're not touching anything or leaning over, like I said before, or touching any metal surfaces. We want to have proper working clearance so we're able to move, and also second, if something happens, we're able to jump back away from the panel and get out of the way if something occurs inside, a malfunction while we're inspecting it. One of the first things I like to look at on these panels is open it up. I like to touch it quickly with the back of my hand, make sure it's not energized, and then open the front cover. And what I want to look at, first of all, make sure there's nothing unusual in here. And then I want to take a look at the panel rating and the label on the panel. So we're going to take a look at that. I'd like to look at the panel label rating just to make sure that it coincides with what I'm seeing that's outside, what I'm seeing as far as main breaker. Now on this panel, one of the first things I want to look at is what type of panel it is. It's a type 1, and it says here indoor load center. Now when you see that and you're standing outside, something's wrong. So it's the wrong equipment if you're seeing this outside the house. And then right here we can see where it says 200 amps max. Now that's the maximum amperage rating of this panel board. So there shouldn't be any single device inside larger than 200 amps. And we don't mean add up all the breakers. What I mean is one single device larger than 200 amps should not be in this panel. And we did see a 200 amp quad main breaker, which is the way that it should be. So this rating plate, if it's visible, I like to look at it just to give me another idea what's going on inside the panel and make sure that everything coincides. So now that we've made sure we have plenty of room to work on this, we're going to take off what's called the dead front cover on this panel board. Now, this enclosure has a pretty big panel cover. We've got 6 screws. Some of them I notice are missing on this board, and that would be something I'd put in a report, that the proper machine head, which means flat-ended screws, should be installed so we have proper fastening of this cover. Now generally when I remove these covers, I like to pull off the upper ones first, and then I can hold my hand, because you kind of have to hold it in place and make sure it doesn't slide down, because you might trip off that main breaker, and that's something you don't want to do because the homeowners typically aren't too happy when that happens. So we're going to pull off this upper screw. Oops. And that happens a lot. Now make sure you hold on to the screws. I like to stick them in my pocket, because if you don't put it in your pocket, what's going to happen is it'll fall behind the wall, or you'll drop it in the dirt if you happen to be outside, and they're gone forever. And make sure you hold on to the cover. You want to prevent it from moving. The last screw is the one that's the most critical. Hang on to it so it doesn't move. Now I like to open it and then hold it from the top, so I've got a handle on it when I start pulling out this last screw. I want to keep it from falling downward and hitting that main breaker. You don't want that to happen. It does take a few minutes. You also want to make sure you have plenty of room behind you. I don't like to have people standing behind me when I'm doing this, because I have to pull it off with 2 hands and be very careful. And you never know what's going to happen once you get it off. So make sure that you're clear. You've got a place to put it. Go ahead and set the cover down. And now we can start inspecting the interior of the panel. So now we remove the dead front covers on these 2 service panels in the basement. Now this is the house where outside we just looked at the meter base and the meter enclosure, and the way that this is wired is we have 2 200 amp panels that are wired in parallel. And outside you notice that that meter enclosure was very large, and that's so that we can get the 2 service entrance cables inside of it with room to bend them and have separate terminal slots for all the service entrance conductors. And what we're looking at here is we have the 2 200 amp panels, and this one is 200 amps, this one is 200. But as you might remember, when we were outside, we looked at the meter, and the limit rating on that meter itself was a 200 CL. So some people might call this a 400 amp service. It's actually 2 200 amp panels wired in parallel with a maximum capacity of 200, which is basically because of the meter. It could be 400 if there was a larger meter put in, most likely, but that's going to be up to a licensed electrician to do that. As home inspectors, we want to just inform our clients of the maximum capacity, and that's of course 200 amps. And you can see here we have the service entrance conductors come into each panel, and on this left side one we have a 200 amp, what's called a quad breaker, and the service entrance conductor itself is a 2/0, what some people call 2/0 or 2/0 service entrance conductor size, which is rated for a maximum of 200 amps. Now let's look at some of the components of the service panel. This outside portion, the metal box, is called the enclosure. The panel board is this component inside where the breakers and the wires connect to. So that's actually the panel board, and the metal component is the enclosure. Most home inspectors will call it a service panel. Some of us call it a panel board. It really doesn't matter, but that's the actual proper language per the National Electrical Code. Now here we can see we have our two hot conductors are feeding in. We have a neutral or the grounded conductor, which is basically the current back to the transformer. And we have, looks like equipment grounds, and we also have here, that's a bonding conductor, probably goes to metal water piping or gas piping. And then we're going to have a grounding electrode conductor, and that's going to be one of these copper wires that exits the panel. At some point we may find that, sometimes we don't. There's times when we have to just assume that there is a grounding electrode, and of course a grounding electrode conductor that's connected to it. We can see it exits the panel, but you never really know where it goes unless you can see it. Now the way the current flows is it comes into the panel through the breaker. We've got this quad 200, and it feeds all these branch circuits through the overcurrent protection devices. In this case, it happens to be breakers. The breakers feed out into the circuits, and then the current flow goes back to the transformer through the grounded conductor, which is the neutral. We have all these terminal slots over here in these what are called bus bars. Some people call them terminal bars. Either one is correct. And on a main service panel, the neutrals or grounded conductors and the equipment grounding conductors, which are the bare ones, will typically all connect together. And we have down here at the bottom, you can see there's a crossbar that connects both of these terminal bars together. Now that provides a path for current flow to go back through the neutral, which is the one traced with the white tape here, to go back to the transformer. We're going to continue looking inside of this enclosure for proper wiring, any potential deficiencies, and so on. And up at the top of the enclosure, we can see that we have several cable entries. And what I'm looking for here is that we have proper cable clamps. Some people call those stress clamps, that we've properly fastened the cables to the enclosure itself. We don't want to have any openings that are going to allow in any foreign objects or small animals and so on. And also I'm looking at the number of cable entries, and we can see up here where we have three cables entering through one slot or one opening, and that's pretty much the maximum that you could have coming through, where you wouldn't have to what's called derate these cables because of heat buildup potential at that entrance. Another thing we can see here is part of the standards of practice for home inspectors require us to identify the wiring method. And this wiring method is non-metallic sheathed cable. Some inspectors call that Romex. Romex is actually a brand name, kind of like Kleenex is for a tissue. So I like to stick with a more generic description, and that would be non-metallic sheathed cable. Now we've been through the main breaker. This is a quad 200 amp in this panel, and then we have full-size breakers on the top. Now the overcurrent protection devices are what we call breakers, and some older homes may have fuses. We can look at those during another session someday. And these are breakers. We've got full size up top, and then the lower half of this type of a panel is typically reserved for or allowed to have what are called mini breakers or twin breakers. If you look at the label, there's typically going to be a circuit illustration, which are a schematic, and it tells you on the bottom where you can put in these twins, and which is what they've done here. This panel is pretty full, and we can see we have some 240 volt circuits, we have some 20 amp circuits. Those would generally be going to kitchen, probably bathroom, maybe exterior. We've got some larger 240 volt circuits here. Those are most likely air conditioning, could be kitchen appliances. So down at the bottom, we've got a lot of 15 amp and 20 amp circuits. These are most likely for what are called convenience receptacles. Could be lighting throughout the house. This is a rather large home, so it's going to have a lot of electric circuits. Getting back to the terminal bars for the neutral and for the equipment grounds, you can see here this panel was nicely done. We have one neutral or one grounded conductor in each individual terminal slot, which is the way it's supposed to be done. Modern construction, we want to have one neutral in a terminal slot, and now for the equipment grounds, we can have up to two in a terminal slot. Now, some older panels you may have three or so, but that was recently clarified in the electrical code about 2-3 years ago, that there should be one neutral only in a terminal slot and a maximum of two equipment grounds in a terminal slot. And this panel is pretty clean. I don't see any foreign material inside. A little bit of sawdust, that's pretty typical. If it was splattered with paint and texture like I see them sometimes, that's not a good thing. And then one key thing to look at on a service panel is that we want to make sure we're protecting the enclosure, this metal enclosure, should it become energized. We want to make sure that we have a path for that fault current to get back to the transformer through this neutral conductor. And right here is what's called the main bonding jumper. We've got this copper strap, and there's a green screw that attaches this neutral terminal bar directly to what we call the can, or the enclosure. So if this thing ever became energized, we don't want that electricity just hanging out there, waiting for a party, which might be you coming along and touching it with both hands. That wouldn't be good. So we want to make sure that we give the current a place to go, and if it flows, the idea is that the circuit breaker that's feeding that circuit is going to trip immediately and what we call clear the circuit so a person doesn't get hurt. So we're always, the idea basically is anything that's metal in the house, we're always trying to keep people in parallel with any type of a circuit that could form. You don't want to be in a series circuit because that means you're the only path. We want to make sure we have a very attractive path for current flow that's parallel to what a human could be touching. And we're still inspecting inside this enclosure and the panel board. Some more things I want to be looking at is the conductors themselves, the cables. We already talked about the wiring type, the penetrations in the enclosure itself. Now, looking at these breakers that we discussed earlier, I want to look at the wire size on these. And we can see here we have a 20 amp breaker, and this is all copper wiring, what I'm seeing inside this panel. It's also a requirement for an inspector to identify the conductor type, the material. So this one, I don't see any aluminum in this panel, any aluminum multi-strand or solid. So this looks to be all copper. So the wiring here is copper wiring. The size of the conductors we want to look at. Now we've got 15 amp breaker. We're going to see here, looks like probably that should be a number 14 copper. So that's typically the smallest size that you're going to see in a house. Up here on this 20 amp one, we can see right there some of the conductor is exposed, and that's definitely a number 12 copper. So that's the proper size. And it's important as an inspector to memorize and have in your head these different wire sizes. Number 14 is the size for a 15 amp breaker. Number 12 copper, minimum size for a 20 amp breaker. Number 10 for a 30, and so on. And when you're looking at aluminum wire, you want to make sure that it's upsized, just one wire size, so it has equal capacity to copper. That's because aluminum's a little bit less of a conductor than copper. So to keep it in a safe zone as far as heat, it has to be upsized one wire size. Now here we're looking over on this side. On this panel board, we have this side is typically called the A side, this side is called the B side. And we can see here we have a ground fault circuit interrupter device. There's another one over here, and typically we would push the test button and then go ahead and check our receptacles that are fed by this, which is usually going to be on the label. On the dead front, we'll put back a little bit later on, and it'll tell you where that circuit goes. Now, as a home inspector, we are required to inspect a GFCI device. The standards that I've read don't require that you actually test it. Some states may be a little bit different. But most inspectors, we do test them. We're going to push the button, and we're going to go ahead and make sure that that circuit is de-energized. And don't forget to come back down and turn the breaker back on. You don't want to leave the house without putting everything back in the position it was when you found it. Also inside, we're looking at the wiring method. This looks to be in good shape. There's not too much wire packed in here. Now, I hear a lot of questions from home inspectors about splices inside of a main panel. And inspectors have told me that they call it out as being wrong, and that's actually incorrect. This enclosure with the cover on is pretty much the same as a junction box. So we are allowed to have splices that are properly done, of course, with wire caps or wire nuts that most people call it, inside this enclosure. Now, if there was a whole bunch of them, certainly I'm going to question that, and I'm going to be looking as to why. That does happen sometimes when it's a panel change out, because what occurs is when they remove the old panel, sometimes the new panel, the breakers are further away and you just don't have enough cable to get to it. So you have to splice in a small pigtail. Other things I'm looking at inside this panel would be any deterioration on the wiring. Sometimes it gets scraped. Sometimes we have conductors that can be exposed because the insulation is damaged. Also, where the screws go in, you want to look at this pretty closely because sometimes there's conductors back here that get damaged, the insulation by the screw going back in. Because we want to make sure when we put this cover back on and we put that screw in, it's not going to hit a conductor and we're going to short out to the panel. Because if you've ever had that happen to you, it's not a lot of fun. It can be a little bit scary. Other things inside the panel, this one here, where we have these two conductors going into this terminal slot, I see this a lot. We've got these two bond wires. I think one goes to probably gas piping. The other one most likely is the grounding electrode conductor. The issue here, and it's kind of a minor issue, but this terminal screw right here is approved for one conductor only. You can pretty much assume that any lug like that or terminal slot is approved for one wire only unless labeled otherwise. Now, sometimes with grounding conductors, we're allowed to install two. So I don't get all excited about it. If this was over here on one of the power conductors, one of the conductors that has amperage flow all the time, that would definitely be wrong. And just a quick recap on current flow. We've got it coming in from the top. This is what's coming from the meter, the service entrance conductors. They come into the panel board through this main breaker. Right here we've got a 200 amp quad breaker, and then that energizes the A bus and the B bus that we connect the breakers to. The breakers feed on out through the hot side, or the ungrounded conductor, to the circuit. The neutral brings back the current into this panel board, and it returns to the transformer through this neutral conductor, or the grounded conductor, which is typically identified by white insulation or a white, what's called a tape tracer. The breakers protect the circuits from not only overcurrent, in other words, amperage that's higher than the rating, like this one here is 15 amps. These breakers also sense heat. So if there's a sustained heat for more than a number of seconds or cycles of electricity, that will also trip the circuit. And here's a blow-up of a typical breaker. This would be a modern breaker. And you can see on the inside where we have the electromagnetic protection, and that's what protects against overcurrent. Basically, the magnetic field trips the breaker from high current flow. And then they also sense heat. So we have a bimetal strip here that senses the heat in the circuit, and that will also cause the breaker to trip if the heat is too high. And then modern breakers will have this arc chamber, which is the arc fault rating of the breaker. Essentially, it has to shunt the arc into this chamber to help prevent the breaker from blowing up. You're going to have an arc when there's a high current flow, and all of a sudden you interrupt it. So that's what that's for. Then, of course, you have your terminals, one place to connect to the bus bar, and then you're going to have another location to connect your branch circuit conductor. So that's it. Pretty simple. Some of the newer ones will have a circuit board inside, but most that you're going to see in residential will be pretty simple and what we call mechanical breakers. The ground fault circuit interrupter devices, those are a little bit different. When they're in breaker form like this, they not only protect against overcurrent, short circuits, and heat, it also senses the amount of current that's going out to the circuit and compares it to what's coming back. And when it's a GFCI device like this, if what's coming back is short even just a small amount like 6 milliamps, this will actually turn off the circuit immediately, so we prevent people from getting hurt. And these are typically used that go to locations where there's grounded surfaces or water, like bathrooms, exterior, and so on. And we have a number of animations we're going to show you that give you that, a good idea as to how current flows, ground fault flows, and what we do with lightning. That's another issue, is what happens if something in the house gets hit by lightning. Well, we want to make sure that we drive it into the dirt, because that's where it wants to go anyway. So enjoy the animations we're going to put together, and we'll talk again. To get a better idea as to how a GFCI circuit breaker works, or a GFCI device, and GFCI stands for ground fault circuit interrupter. Some people just simply call it a GFI, and that's fine too. What we have here in this illustration is a typical 20 amp breaker, and you can see it has a push button to test it, and some inspectors test them, some don't. We're required to inspect them. You don't have to test them. I would make sure that you know what's plugged into it before you do that. Anyway, we have a typical GFI breaker here, and we have the hot out, which is going to be the black or the red wire, which connects to the small slot side of the receptacle. We then have the neutral, which is the return current back, and then we have this green, which is the equipment ground. Now, what a GFI does is it constantly monitors the circuit flow. In other words, what it's always doing is checking to see is what's going out on the black. Let's say it's 8 amps, that we always have 8 amps coming back, because the current should always be equal. Voltage is going to change because the voltage is the pressure, and that's what we use to drive our components. Now, you'll see on the GFCI breaker that we have this pigtail that comes with the GFI breaker. These are always connected, and then the black for the circuit and the white for the circuit connect to this breaker. The GFI basically inside is a small amp probe. It measures amperage flow constantly. And if there's any leakage, we know that what's coming back is going to be less. So let's say we have the 8 amps going out and we have not 8 amps coming back. If there's a differential of 6 milliamps, this breaker will then trip. So it protects people who are in potential contact with that circuit from getting hurt. So the GFI just basically monitors the entire circuit flow while it's being used. And an AFCI is very similar, although it is definitely not the same protection. So don't confuse AFCI, arc fault circuit interrupter, with a GFCI, ground fault circuit interrupter. They're completely different, but the AFCI does the same thing. It monitors a circuit, but it's monitoring for a wave pattern and not amperage flow. And here we have a typical AFCI breaker. And this is what they look like once they're installed from the front. They typically have a blue test button. Now here's one with the cover removed, and you can see inside there's a lot of circuitry. So an AFCI breaker, similar to a GFCI breaker, not only does it provide the typical circuit breaker protection for over amperage and also heat, it provides protection for the circuit itself. And you can see here on the right, an AFCI breaker does come with the neutral pigtail, and the neutral wire from the circuit has to connect to the breaker, as does the hot. So what this breaker does is it has a small little circuit board inside that continuously monitors the circuit waveform. And what it's looking for is any unusual pattern that would indicate an arc is about to or is occurring. And most modern arc fault circuit interrupters are what are called combination arc fault devices. Now this doesn't mean that they provide combination AFCI, GFCI protection. What it means is that the AFCI is capable of sensing a parallel or a series arc fault. Now a series fault would be an arc occurring between the same conductor, and parallel would just mean that it's an arc that's occurring between another conductor or another surface. So that's what combination means. So AFCI is completely different from GFCI protection. So with circuits that would require both, you'd have to put in both types of protection. And right now I can't think of any circuits that require both. And now we're going to look at several illustrations from Bruce Barker's book, Everybody's Building Code. If you like the illustrations, you can get them in his book at everybodysbuildingcode.com. Now this is a typical setup for electric service. We've got over here on the left a transformer up on a pole. We also may see them in a vault, or they can be on grade at the house or at the street. Now electricity, the current, comes from the transformer. And we create the neutral conductor right here at the center tap on the transformer. If you looked inside, it would be labeled XO. And we simply ground that conductor, and that's what creates the grounded conductor, what many people call a neutral. So this is our source up here, and the electricity comes into the house, this case through the masthead, and it goes to the meter enclosure, and then feeds the service equipment. In this case, we have a service disconnect. And then it goes to the primary panel board. From the primary panel board, it will go to the load. Now, the load just means a device that uses electricity. That could be a washing machine, it could be any electrical device. Now, when current flows, contrary to a lot of an incorrect belief out there and myth, electricity goes through the load, and then it always wants to go back to where it came from, which is the source up here at the transformer. It does not want to go to the ground. The grounding electrode is simply to reintroduce the earth reference to ground for the grounded conductor. But more importantly, this grounding electrode is to direct lightning that may hit the house or nearby back into the dirt where it wants to go. And we'll get to that later in another slide. So let's look at what happens when current flows through the house. I've got a simple animation here. This little star up here on the left represents electricity. Now it simply enters the house, it goes through the load, returns back to the transformer through the neutral. It's a very simple circuit. Obviously it needs to be a loop, so we need to have a complete circuit all the way back to the transformer. And that's the normal flow for electricity. Now when we have abnormal flow, that's called a ground fault. And what happens there is we have these components can become energized that are not an intended part of the circuit. And that's why we bond everything together with a bonding conductor. Also can be used is the grounding conductor, that's the equipment ground, that bonds all these pieces of metal together. So we have a path once again through the neutral conductor back to the transformer, so the electricity can go back where it wants to go. Just think of it, it always wants to go back home to mama, and that's the transformer, which is the source for the electricity. In this illustration, we want to look at what happens when there's an external surge in the electrical system. And most of the time that's caused by lightning. And it could be an indirect or a direct hit. Most of the time it occurs at the transformer, which is going to be outside at the pole. Sometimes it'll hit the masthead if there is one in the house. Of course, most modern homes will have an underground lateral feed. Now, when you have a lightning hit or an external surge, what happens is very high voltage enters the house. And essentially what we want to do is give it a place to go. And lightning, as we all know, is basically positive ions and negative ions, positive being in the sky and the negative being in the dirt. And essentially they just want to get together really bad and party. So that's why lightning occurs, and the ions can get together, and it causes that big huge arc and high voltage. And a hit could be maybe even 100,000 volts. So what we want to do in the house is provide a place down here, the grounding electrode, which is a piece of metal basically in the dirt, sometimes embedded in the foundation when we use a concrete encased electrode, otherwise known as a UFER. And what we're doing is we're really just giving this lightning, this surge, a place to go. And you can see here at the pole transformer, when there's an external surge, what will happen is the current will travel into the house, and we're just going to send it to the dirt. So it's real simple. All we're doing is providing a place, and the pole already has one grounding electrode conductor and grounding electrode where most of this voltage will go. But of course, electricity being what it is, it's going to take every available path. So some will go into the house, and what we do with the service equipment, which is where we always should be connecting the grounding electrode conductor, we're providing a place for this lightning to get back into the dirt so it can go ahead and have its party. And that's much better than the lightning trying to release inside the house and get to the dirt, where it's going to cause a lot more damage. And essentially this is the same thing that a surge protector does that you probably have on your computer. And it essentially shunts a voltage surge greater than 120 volts to ground, which is the grounding system, and then back into the dirt. So that's where lightning wants to go. And essentially really all we're doing is giving it a place and a very attractive path to get there, so that most of this surge will go ahead into the dirt where it wants to go anyway, and it minimizes the damage inside the house. In this slide, let's look at see what happens when there's a ground fault. Now, a ground fault basically just means that we have electricity or current that's leaking, and it'll leak to an unintended part of the construction. So obviously electricity will leak to metal components because they're conductive. So when you have a leak, basically we have electricity squirting all over, kind of like a plumbing leak where you would have water squirting all over and create a condition where everything gets wet. Well, with electricity leaking, let's say on this slide over here at a load, at an electrical component, we have electricity that's leaking to, let's say, the case of the equipment. And a good example of that would be a clothes washer, where we have maybe some damage to the flexible cord where a couple of strands of that conductor are touching the case of the equipment. Now what happens is the case of the equipment becomes energized. And that electricity, as we remember from one of the earlier slides, has only one purpose, and that is it wants to return to its source, which is over here at the transformer. Now when we have equipment grounds that are properly connected, and we have a fault over here at the load, the primary low resistance return path is going to be the equipment ground back through all of our electrical equipment. So this is the primary reason we need to have equipment grounds, and that equipment grounding conductor connects back at, let's say, a load center or a panel board, and it connects again back at your service equipment, and then all the way through the meter, and it provides a low resistance, meaning very attractive to electricity, like metal, copper, or aluminum conductor, and that current can get back to where it came from. That's all it wants to do, and it'll do that through any path possible. So a fault is basically a leak of electricity that's trying to get back home to where it came from. Now the secondary path, which is a very high resistive path because the dirt does not conduct electricity very well, is going to be here at this secondary high resistance return path, where the current will try to get back to the equipment grounding conductor for that transformer to get back to where it came from up here, or at the pad transformer at the street, or wherever it is. So the primary path is here, inside the house, and then back through the service entrance conductors to the transformer. Now the benefit of having this path is that it allows the electricity to travel. So when that current travels, it alerts in this panel board here the overcurrent protection device, which might be a breaker, it could be a fuse, that there's current traveling that is unrestricted. So the current will travel as much and as fast as possible, and that's why we have breakers, which will open the circuit, so disconnect, and perform what we call clear the circuit, so that we're not energizing all these components and waiting for a person to come along and actually touch that and maybe touch a grounded surface and be in what we call a series circuit, which is not good for a person. And that's why it's so important that we have this equipment grounding conductor be continuous and have complete continuity all the way back to the transformer. If we don't have that, and one of these components becomes energized, there is no path for the current to flow. So if it doesn't flow, this component could remain energized and it's just waiting for somebody to touch it or something to occur, which could hurt somebody. So equipment grounds are very important to be connected. And the reason we like to keep them separated from the neutral in a sub-panel is so you don't have parallel paths going back. You want to keep it on the equipment grounding conductor. That's what it's designed to be. There should be no current on the equipment ground unless there's a malfunction. And it should be pretty quick and immediate that a overcurrent protection device will trip and go ahead and what we call clear the circuit. So that's a ground fault, is basically just a leak of current to an unintended path, which are metal components in the house. And that could be water piping that's metal, it could be gas piping, and that's why we bond everything to the service equipment to provide a path for the current flow, again, back to the transformer. It really doesn't like the dirt because that's a high resistive path. Sometimes electricity will travel in the trench between the house and the pole along metal water service pipes, and that'll give it a place to go and get back up to the transformer. But most of them now are going to be plastic. So this is very critical, the equipment ground. This is the right side main panel. Again, we're still looking at this parallel service panel setup. And this right side panel, it looks like it was installed pretty much just as sub-panel feeds. We've got two 100 amp breakers in here that are protecting sub-panel feeders. And we can see it looks like here a 15 amp breaker that was added probably just for a convenience receptacle. It looks like a different cable clamp up here at the top, so most likely was added later. Now, I want to take a look at these sub-panel feeds. What we should be seeing is a 4-conductor feeder that goes to a sub-panel. We want to have 2 hots, we want to have a neutral, and then we should have a separate equipment grounding conductor that comes back to this main panel. We've got a sub-panel feeder that enters the top of this panel board through the enclosure. We have a cable clamp, and what we want to make sure is that we have a 4-conductor feeder. And on this one I can see we have a hot, so we have our 2 hots we should have. We've got a neutral conductor, which is insulated, and by the way, the neutral is insulated because it does carry current. And then we have an equipment grounding conductor, which is typically going to be a bare copper or bare aluminum. Now in this case it happens to be aluminum. So now we can see in this home we do have some aluminum wiring. It just wasn't in the other panel, it's in this one. And this is multi-strand aluminum. It's safe if installed properly. We use it all the time. It's great stuff. Now on the sub-panel feed, we should have the neutral terminal bar over here, and we can see where the neutral conductor terminates here. And we also have the equipment grounding conductor. And this is the proper way to do it. At the main panel, both the neutral and the equipment ground connect to the same terminal bar, not in the same terminal slot, but the same bar, because they're both going to take the path back to the transformer through the neutral conductor. So this is the proper way to originate our feeders for a sub-panel. You can see that there's 2 of them. It looks like, I believe this one on the panel label went out to the exterior sub-panel we looked at earlier, and this one I believe goes to a garage sub-panel from what I recall on the label. Okay, now that we've inspected these panels inside, we need to make sure that we get the dead front covers installed back properly without tripping any of the breakers, because we don't want to have that happen. Homeowners don't like that. So we want to be careful. Pick the panel up. I like to have the door open, obviously, so I can see where the breakers are going to align in the slot. And I can see that this one right now is upside down. So we have to change it this way to make sure it fits properly. Now, you want to hold on to it with one hand and make sure you're not tripping that main breaker. Now, a lot of these big ones tend to twist out like this. They're kind of a pain. So you want to get in one of the upper ones. Just start the screws first. I like to get the 2 upper ones in first, so I make sure it's not going to be twisting on me. And you can see how that cover likes to move around on these bigger panels. There we go. So get it aligned and go ahead and get a bottom one in. This type of a panel, they're a little bit of a pain, but you want to get it started. So get your screws started so you're sure it's not going to be flopping around on you. And you can go ahead and let go and grab your screwdriver and start driving things home. I like to get a couple of opposing sides in first to kind of hold it so it's not twisting around. Like I said before, this type of a panel, the covers like to twist and deform a little bit on you. So go ahead and get your screws in. Now this one was missing a couple of screws, so I just put in basically what was there, and I'll make a note to locate the other screws and install them. Not a big deal. And there we go. Close it up. And we have one more to put back on. And now we're at the garage sub panel. And one of the things we want to look at with any type of a panel is the labeling of the circuits. Now we can see here we have a number of breakers. They're labeled sunroom plugs, sunroom lights. That's pretty clear. All of these labels should be referencing what's called a permanent landmark. Now here we have den plugs. I think we can figure out what the den is. And then we go to this one here that says computer plugs. That's a little bit vague. I'm not quite sure what computer plugs is. I'm not quite sure that a homeowner could figure that out either. So I'd recommend a more permanent type of a landmark reference for this switch here, for this disconnect. The rest of them are pretty clear. We've got water heater, bathroom, AC for air conditioner, floodlights, I'm presuming that's outside somewhere. So the remainder of these are pretty clear. We've got dryer. And then I notice here that we have two arc fault circuit interrupter breakers, which would have been at the time this house was built, maybe 10 or so years ago, would have been required for the bedroom circuits only. And that's pretty much where they go, up bedroom lights. Now we've got our cover off and we can look inside this sub panel. And we're going to take a look at where the cables are coming in. One of the particular things that we want to look at in this sub panel is our separation of ground and neutral conductors. Now here's our feeder that's coming into the sub panel, and I can see we've got our two hots which loop around the top, our neutral conductor which comes up here and connects to this neutral terminal bar. It does look nice and clean. We've got one conductor in each terminal slot. Same thing over here. These two neutrals are connected together by this tie bar that's inside the top of the panel. Here we've got some more neutrals. I see one conductor in each terminal slot. Looks to be in good shape. And then over here, this is a bonded grounding terminal bar. It's generally an extra part that you have to purchase for the panel, and all of the equipment grounds connect to that. And that terminal bar is bonded, which means electrically continuous with this enclosure. So we're not only protecting the circuits, we're also protecting this metal enclosure. Should it become energized, we want to make sure that we're providing a path back to the main service panel downstairs and then to the transformer from this sub panel, which some people call a distribution panel, by the way. We've got these arc fault circuit interrupters we looked at before, and you'll see on the arc fault circuit interrupter we also have two neutral wires connected to it. That's because, just like a GFI, the arc fault circuit interrupter has to monitor the entire circuit. So it's monitoring the circuit flow as it's being used by the upstairs bedrooms and making sure that there's no unusual waveforms in the circuit that are telling this device that an arc fault is about to occur, which is electricity basically traveling through the air, and that's not good because it's going to probably burn the house down. So that's what these devices do. Some inspectors test them by pushing the test button. I typically only do that if it's a vacant home, because if you push these, you're going to turn off everything upstairs in the bedrooms. And most people don't like that when they come home and all the clocks are doing this thing, reset me, reset me. So the rest of this panel inside looks good. We've got cable clamps coming in on everything. So a pretty clean panel, proper wire size. We have an insect over here. Looks like he's going to be there for a long time. We've got 15 amp breakers, proper size wire, 20 amp breakers, proper size wire. The clothes dryer circuit I can see is a number 10 copper. So looks perfect. This is a nice panel inside.